are part of the SLAG survey. This is the website, and this is the main paper of reference. And this is in honor of the banana slugs that you will hopefully see in the campus here. And what we did, we observed with the Subaru telescope and the Keck telescope globular cluster systems around elliptical galaxies. And the data are public, and so you have access to radial velocities for thousands of globular clusters around elliptical galaxies. And the reason why we want to study globular clusters and galaxies is because this is a globular cluster, and as you all know, these objects are very compact, they're old, therefore they have a very high surface brightness, so they're easy to observe in the Locking universe. And there are a lot of globular clusters around the giant elliptical galaxies, thousands of thousands. And so you can observe them at tens of effective radii from the galaxy center. And another great property of globular cluster systems is that they are bimodal in color or metallicity. This means that you have two globular cluster subpopulations living in the same potential well of the underlying galaxies, but they behave very differently from each other. We have one population, the red globular cluster population, which is probably more connected to the stellar halo of the galaxy, and then you have the metal-poor globular clusters, which are probably more linked to the halo of the elliptical galaxy. And this is an example of what I was talking about. This is a color magnitude of a globular cluster system in this galaxy. And you can see that there are two big sequences here, one at red colors and another one at blue colors. And if you manage to separate these two subpopulations, you can work with these two globular cluster subpopulations separately. And why do we want to do this? There are many applications from these globular cluster bimodality to galaxy formation, but here I really want to focus on one. And the question we want to try to tackle is this one. What is the inner slope of dark matter profile in elliptical galaxies? So is it a cusp or a core? So far, people have given talks about cusps and cores in dwarf ellipticals, and the reason is very simple, because if you assume that the total mass of the galaxy is made by the stellar mass plus the dark matter mass, in dwarf galaxies the stellar mass we say is negligible with respect to the dark matter mass. So you can just ignore this term and you can just focus on the dark matter mass. And in big ellipticals, this is not true anymore, as we all know, because the stellar mass is not negligible anymore. And not only is not negligible, but is also very uncertain to measure. And this is due, of course, to the uncertainties on the IMF. However, we still want to try to measure and see if and at which level we can measure the inner slope of the dark matter profile. So you can also form cusps and cores, of course, in elliptical galaxies, very similar to what you do in dwarf galaxies, but instead of supernovae feedback, you have AGN feedback, which can cause cores, can create cores in the centers. But at the same time, you can also create cores with self-interacting dark matters by fine-tuning the cross-section of the dark matter particles. And in this talk, I want to tell you how we try to measure this slope. So either 0 or 1 or something in between or something even more cuspy in one particular galaxy. Before we do this, this is a summary of the cusp of the inner slope of dark matter profile in a bunch of literature galaxies. So these are dwarf spheroidals. These are galaxies from the Things, dwarf galaxies from the Things survey. These are still dwarf galaxies from a recent paper of Adams et al. 2014. And these are big BCGs from Newman et al. 2013. And up here, this is a data point. This is M87. And very recently, Agnello et al. Measured that apparently M87 has a central cusp in the center. So not only is much steeper than a Navarro-Franken-White with a slope of 1.6, which is huge. And you can see here that there is a void here is where big ellipticals live. So I want to talk about a galaxy with a virial mass of about 2 × 10⁻³ virial masses, and we want to try to measure gamma. Okay, and this is the galaxy I'm going to be talking about. It's 23 megaparsec away. This is about 270 kiloparsec across. The center is saturated. This is another nearby galaxy. And very likely at the center of this galaxy there is an AGN, which is probably still active. And so if is AGN, which creates central cores in elliptical galaxies, we should hopefully able to measure it. How do we do this? There is a big problem. The problem is that the equations we use and the theory behind it is very degenerate. And there are two big degeneracies happening here. There is the mass anisotropy degeneracy, and this is the these are the Jeans equations for a spherical galaxy, and these quantities are somehow related to your observations. So you can measure nu, and you can somehow also try to measure sigma r. But what you cannot measure, or at least what is very hard to measure, is beta, which is linked to the orbits of the stars or the trace particles in the system. And what you also don't know is the total mass of the galaxy, and this is what we want to try to measure. And if you take this term now and you decompose it into their components, you can also see that there is another degeneracy here, because in order to get m tot constant, you can just trade these two. You can just have 80% of stellar mass or 20% of dark matter, or vice versa, and you can keep this number here very constant. So the big problem with measuring cusps and cores in elliptical galaxies is, of course, m star. So let's see what we can do. There is a small trick then that we can apply, and the trick is this one. If you draw a dark matter profile applying this equation here, you will have a range of dark matter profiles. This is cumulative dark mass as a function of radius for the Carina galaxies taken from this paper. And you can see that there are very large uncertainties here, but the uncertainty is minimized at one particular radius, which is, in this case, about the half-light radius of the galaxy. So this means that it doesn't matter really what the galaxy is doing here, or what uncertainties are. What really matters is that there is one particular radius that people usually call a sweet spot, or pinch radius, where uncertainties are minimized. So what you can do, you can use the fact that within one galaxy we have multiple populations in equilibrium, like, as I told you, the red Gerber clusters, the blue Gerber clusters, and the stars, of course, and we can try to model them separately, and then combine the pinch radii from all these tracers in order to constrain the dark matter mass. Okay, for reference, this is the stellar mass of this galaxy, and as you can see in dwarfs, you can confidently state that the stellar mass is negligible with respect to the dark matter mass. Okay, so let's go back to our test galaxy. This is the galaxy at the center, and what we do, we model, we apply the Jeans equations to the stars, which concentrate at the center, to the red Gerber clusters, which are slightly more extended, and then to the blue Gerber clusters, which are way more extended than the stars. and red Gerber clusters. And for reference, this is simply the velocity dispersion profile for the stars in gray, and for the blue Gerber clusters in blue and the red Gerber clusters as a function of radius. And you can see how the blue Gerber clusters, the velocity dispersion of the blue Gerber cluster seems to go up and then reach a plateau here, while the red Gerber clusters seem to have a decreasing trend, although a bit bumpy. Okay, so we apply the Jeans equations to this system, and we get some dark mass profiles, dark matter mass profiles from the Jeans equations. Before doing this, of course, we need to model the stellar mass, and we do our best to model the stellar mass most accurately as possible. We compare our stellar mass to population synthesis predictions, of course, and we get a stellar mass which is quasi-salpeter, not almost salpeter, but if you assume that the IMF varies with sigma, I don't know if there will be discussions about this galaxy should have a salpeter or super salpeter IMF, whereas we find somehow a smaller IMF, quasi-Krupa, quasi-salpeter. Okay, so these are my results. This is what happens if you model the stellar component. This is dark matter mass, but I also show the stellar mass here for the stars, for the red Gerber clusters, and for the blue Gerber clusters. Okay, and these are the 1 sigma envelope. And you can see, first of all, that the uncertainties again are minimized here at the pinch radius of the stars and of the red Gerber clusters, which are very similar. And whereas for the blue Gerber clusters, the uncertainties are minimized up here, way at about 100 kiloparsec from the center. So if you assume that there are these 3 tracers within the same galaxy, then there is an underlying dark matter profile, an underlying dark matter potential which supports these 3 tracers simultaneously. So the true dark matter profile will be the one which can fit these 3 profiles simultaneously. So what we're doing is simply measuring the joint, the joint solutions for this problem. And this is what I'm showing here. So this is the way we parameterize the dark matter profile. So it's just a generalized Hernquist profile. And gamma is what we want to measure. And in black here are the combined solutions. You can see that without combined solutions of the single tracer are completely unconstrained. But if you use the joint solutions, you can see something interesting. First of all, that gamma seems to be consistent with 0, and at least seems to be 1 sigma, more than 1 sigma away from a Cusp and Navarro-Franken-White. Sorry?
What's the probability? Black one is what probability?
The black one are the combined chi-square solutions from the 3 tracers together, the joint solutions.
Should be minus 0.8, right?
You mean up here? Yeah, sure. I mean, no, don't really look at the solution here. You should more look at the range. Let's say that at this stage we can say that at least at 1 sigma level we can exclude a Navarro-Franken-White.
1 sigma level?
Yes. Well, slightly more than 1 sigma. This is the 1 sigma envelope. And
exclude anything on 1 sigma level?
Sorry?
How could you possibly exclude anything on 1 sigma level? We don't need to take 3 sigma levels or something?
Yeah. Okay. But this is, however, only for fixed. I guess we can. I don't have much time left. Yes. And I just want to show you a comparison with X-ray studies, because comparison with mass, with dark mass estimates from X-rays are usually not very good for elliptical galaxies. So here I'm showing our best solution in orange, and the profile, dark matter profiles. This is actually in terms of circular velocities for this galaxy. And this is our X-rays, and these are our solution, which compared to other galaxies agree very well. We are on the right path, I believe, but there is a big problem, and the big problem is stellar mass, because if you change just a little bit the stellar mass, this will change all your solutions. Assuming a Krupa IMF would give you a Cusp central dark matter profile, whereas larger IMFs, so salpeter or super salpeter, will give you more and more chord profile. So until we have a really good handle on the stellar mass, we cannot be sure about the gamma in elliptical galaxies. And that's all. Thank you.
Thank you. Okay, so maybe time for one, two questions. However, you want to continue the
Could you
discussion?
explain how to exclude X on one signal?
What he just mentioned, on a 1 sigma level, this is the result. So he admits that it's only 1 sigma result.
Yeah, so sure. No, absolutely.
He doesn't say 3
No.
sigma, so in that sense he's fair. That's my personal view on this. You might not like 1 sigma, but it's your business.
Yeah.
Okay, it is good, yeah.
So it looked to me like as you went to the cusp of your favorite solutions, your scale radii were getting pretty big. So if you looked at just, say, the implied concentration, I mean, it seems to me like that concentration would be huge and kind of
Yeah. Yeah, there is a big degeneracy here. I mean, the contours are very elongated here, as you can see, and the average concentration is 20. But if you include the error bars, of course, they go up to 50 or so. It is a worry, and it's also a worry the fact, for instance, that you have another degeneracy here of the scale radius, of course, becoming larger and larger. But yeah, let's say that the concentration is in the same ballpark as other results.
Okay, so
Thanks.
Thanks very much. We have to continue. We have